First time for me for the last 2.5 years. So 2.5 years not traveling, but it's such really a pleasure to talk to people and see people again. So sadly that not every one of you were able to travel here and to attend this meeting face to face. So, but the hybrid arrangements, I think, so will be something of the future, I assume, anyway. So thanks. If you can go to the next slide. So just a really quick introduction to the EuroSwac project. As said, it's funded by Interreg from General Marché. It's a 3.5 million pound project. 2.3 million of this is funded by ERDF. We have a total of 11 partners there from France and UK. You can see them on the bottom there: Exeter University, the University of Plymouth, National Lobster, Hatchery, Ensta, NKE, EDF, ClubSWAC, Doris Engineering, Doris Marine, Oceanide, Doris. So I think so. All the partners are presented here, and some of them will, as I said, will present the results what have been achieved in the last 9 months. So overall, what we are doing here is looking at the design and validation of seawater air conditioning systems. We're looking particular in the cost efficiency, so trying to reduce the cost of the installation of the seawater air conditioning systems so they can be replicated along the shorelines. Part of this is looking into innovations to reduce the cost, and again we will have some presentations around the innovations, but also we look in terms of the optimization to reduce the cost and enhance the efficiency. Overall, of course, we have to look into sustainability and suitability there as well. So looking in terms of regulation aspects as well there to enable, again, the cost-effective installation of the SWAC systems. Okay, if you can go to the next. So the project is split into 4 tasks or work packages. One is on environment, one is on the flexible or on the innovation part, I should say. The third one is really in terms of the demonstration of the technology, and the fourth one is on the optimization. And as I said, we will have 4, I think, so very interesting presentations of the outputs, what has been achieved so far. And at this stage, I would like to pass over to Konstantinos Georgioulis from the University of Plymouth. Before I do this, I maybe should say, please, if you have any questions, because it's a hybrid system, maybe type them into the chat box while speeches are ongoing. Otherwise, you know, afterwards there will be some question time. So raise your hand on the online system. Of course, you know, you can raise your physical hand here, so we can then answer the questions. So that's all for me at this point. So over to Konstantinos.
Just for the French speakers, if you have some questions in French, you can also ask, because a lot of people here are speaking French. So
You can also say French if you want.
oui, d'ailleurs, je peux le dire en français aussi. N'hésitez pas à poser vos questions en français également. Il n'y a aucun problème.
And Caroline?
Yes.
Apologies, Frank has said, and I agree, is there any chance we can make the PowerPoint in presentation mode, because it's quite small on our screens?
Okay.
Sorry to give you another IT issue.
No, I can do that.
Thank you.
Yes, but I open the other one. Is it good this way?
Yes, that's better. Thank you.
Okay, great. Oh, here you are. Okay, let me.
Hi everyone, thank you for being here. So I would like to update you on the work we're doing at the University of Plymouth for the environmental impact assessment of the seawater air conditioning system. To begin with, I would like to mention that we have two sites at the UK that we're looking into. One of them is the Brixham Laboratory, and the second one is the National Lobster Hatchery at Newlyn. So we have 5 tasks that we're looking into. The first of them is to find out and investigate the environmental constraints that are regarding the seawater air conditioning system. The second of them is to model and see what kind of impacts the SWAC system can have on the surrounding seawater based on using computational fluid dynamics. Furthermore, we also want to investigate how we could optimize the SWAC system and see its potential for aqua farming, and finally find out all the necessary permits and licenses that someone would need in order to operate a full SWAC system either in the UK or in France. So in the following slide here, we can see that this is the first of the demonstrator sites of the UK. This is the Brixham Laboratory, which is affiliated to the University of Plymouth, and there we already have the SWAC system, but it has not been run for a lot of years. So our first task is to reawaken it and evaluate how it works, optimize it, and find out a little more about the system. The second one on the following slide is the National Lobster Hatchery at Newlyn. Currently they do not have a SWAC system there, but they're interested to see if one would be appropriate for their needs. Following, I would like to go back to Brixham Lab and give you a little more details about what we have there. So as I said, we already have a SWAC system, and on the picture in the middle we can see a screenshot from Google Maps. It's just showing the location of the 2 intakes that we have that abstract water for SWAC and any other purposes of the lab. And the red dot is where the discharge is currently. Based on the water, it can be either above surface in low tide or submerged if the thing high tide situation. So on the right, it's something similar. It just shows the bathymetry. It's colored based on the depth of the waters. And the black dots are the location where NKE is going to install buoys for us to measure the water quality during, before and after the operation of the SWAC system. And following, yes, so here it just gives a little more details about what we're going to measure using the probes provided by NKE. So based on our literature review and what the probe would actually do, we identified a few parameters that we would like to measure. So we'd like to know the depth, we'd like to know the salinity, the acidity of the water. The temperature is obviously very important for SWAC. Yes, and this is having, and we also are going to deploy a boat, so we're going to be able to move one of the buoys around in order to capture a bigger area. And on to the second task that we are doing at the University of Plymouth, which is about computational fluid dynamics. So we are mainly focused on doing a numerical modeling investigation to find out to investigate the discharge dispersion of SWAC effluent. So for that, we are using a Reynolds average Navier-Stokes solver, which will give us a transient simulation. Now, in order to have a more macroscopic view of what is happening around SWAC effluent discharge, we are using also an analytical model just to give us a steady state simulation, which is not as accurate as CFD, but it can give us a wider view. Now, both of these models will be customized for the sites in the UK and France as well. Here we can see some early results of the CFD solver. This is a 2D case. What is interesting here is at the right, there is a discharge that is discharging water at 10 degrees higher than the ambient temperature. And the screenshot just show what would happen in low, mid, and high tide. Now for this simulation, it's very simple. There's no current and there's no wave in the domain. But if we go on to the following one here, it is a three-dimensional one where we also have current in the domain.
Yeah, but we won't. Something is crossing it. Well, I know people want it. Sorry, you're experiencing a new fish. Okay. It's something else. Okay.
Okay. Yeah, so here we have a 3D case where we also include the effects of current in the domain. So these are three sensitivity tests where we increased the current velocity in the domain. There is a discharge that is throwing water into the surrounding numerical domain at 10 degrees higher than the ambient temperature. And this is something that we're going to build on and potentially include the effect that the waves can have on the effluent as well. And in addition with safety, as I mentioned, we are also looking into a more simple analytical model. To give you a quick summary, just the way it works is just takes inputs regarding the effluent, some ambient conditions, and a very simple geometry, and produces a report based on the effluent characteristics. For this presentation, we just have a case based on July 21, when we identified that there was a spike in the ambient water temperature. And based on the regulations, that would give us only an excess of 2 degrees that we would be allowed, that the effluent would be allowed to have at the end of the mixing zone. And at the right is just the results showing that this was achieved within 2 meters of the discharge. The water quality standards were met. Now this was only 2 meters because the flow rate at the Brixham lab is supposed to be very low, and this model is just going to be more useful in order to talk with probably environmental agencies to show that what we are doing is within the regulations, and it's going to be very easy to change the configuration, change the inputs, and evaluate different cases. Moving on, our third task is to optimize the SWAC system. But in order to do that, first of all, we would have to run the SWAC system that we have at Brixham. And here we have a schematic that shows how our system is configured. So in the at the left is just the position of the pumping station where we have 2 pumps that abstract water, and the middle is a simple schematic that shows the how water is going from this pumping station throughout the system and at the heat exchangers. So we're also looking how we can reduce the impact that the SWAC system can have on the environment. We also have been in talks with DeProfundis, and they have suggested a few different things that we can do to optimize our system. And quickly to summarize them, that would be to either increase the pipe diameter so we have more flow rate, to use a booster pump, an automatic pump frequency regulator, or potentially installing a reversible heat pump. Finally, another thing that we are looking into is how we could use the stock discharge effluent as an intake for other activities in the laboratory. So instead of throwing directly into the sea, just using it for other purposes, and that maybe have economical or environmental impacts as well if we can reduce the temperature of the effluent. So the next task is evaluating the potential that SWAC system can have for aquaculture farming. And the National Lobster Hatchery is leading this part, and they are producing a report to find out how this can be done. It is important to say that this is going to be very depending on the species, because for a lot of marine species, even small changes in their ideal conditions like temperature, water salinity, acidity, can have very, very big impacts on them. And our last task is finding out the permits and licenses that someone would need to run a SWAC system. So here is a simple flow chart showing what would be needed in the UK. So if there's a new SWAC system, there's going to be construction to lay pipes and do work in the sea. So that would first of all require authorization and a marine license from the Marine Management Organization. And typically that would take between 13 to 15 weeks from the time of assigning a JS officer. Along with that, an environmental permit would be needed, either for abstraction if the flow rate is larger than 20 cubic meters per day, and also for discharge, where there's thermal and other pollutant criteria that have to be met. This is done by going through the environmental agency, who are also responsible on identifying the length and the size of the mixing zone that will be appropriate on a case-by-case basis. And finally, we have also, this is a work in progress, but we also have looked into the French regulations. And this is a quick summary of what we have so far. So someone would, in France would need to be working in operation of within the Water Act of the Environmental Code. And also, it is important, in most cases, an environmental impact assessment would be needed, especially if the flow rates if the flows that are involved in the SWAC system are higher, larger than 30 cubic meters per hour. Finally, because there's going to be work laying pipes on a public domain authorization by the authority that holds the rights for this domain that have to be taken. For listening, I'm very happy to answer.
Okay, thank you very much. Again, it's really nice, yes. I'm just looking at the chat box. There's nothing in the chat box, but I'm opening up the floor for any questions. So if there are no questions at the moment, then I maybe start. So thank you very much for this very interesting presentation of this work there. How do you think will your work influence maybe the regulatory bodies like NMO? So what do you think, how can we, when it's all about efficiency and cost effectiveness, so how your work potentially can enhance really the installation processes and reduce maybe the EI requirements?
I think through modeling the impacts that the SWAC system can have on the environment, we can show that we can stay within the regulations. We can show that the impact it has on the environment is within the spirit of what the law says. So essentially, we can show that the SWAC system the impacts it has on the environment are within what the law says, what the law says there. So maybe at the future it will be easier for someone to go through this process of submitting an environmental impact assessment and obtaining licenses to operate in the UK in France.
You can ask them, are you in active engagement with regulatory in France, maybe, or in the UK as well, to do, inform and present these results, so they actually see the outcomes and consider maybe.
We have been in contact with MMO in the UK, who are mostly responsible about the marine license applications. So, we have been in contact for the past few months, and I think they were happy with the first report that we saw to them, but it's a process, so we're still talking.
So they're engaging.
Yeah,
and
so we-
potentially consider.
Yeah.
It's very good to hear. Any other questions from the audience, online or in real flesh? I think so. Okay, then we might go to the second presentation.
Yes.
Just hoping it all works.
Is it possible to have the baseline bigger?
Trying something. Is this better?
On the screen, I think so, because it's quite difficult to read.
This is
I think that if you share all the screen, then you can see.
really can. This-
Oh, this- Okay.
Even if I'm the only one by one country.
Okay, so next speaker is Bruno. So Bruno, the floor is yours.
Thank you very much. So the current project is about using SWAC in the Channel region. So it raises the question of doing SWAC in temperated regions. If I tell you about the SWAC system, the first idea that will come to you is this one. You see a tropical island with water that is pumped at 1,000 meters deep. The water, when it's at 1,000 meters deep, its temperature is about 4 degrees. So when you pump this water, you can directly air condition a building without doing anything. And the beautiful picture of a tropical island is Bora Bora, the Intercontinental Hotel, who is cooled with an air conditioning system. But when we are in temperated countries, we don't have the same things. Here you see in the channel the difference between air temperature and sea temperature. You see on both screens, on both graphics, you have different colors for the different hours of the day. So there is something obvious. The yellow means noon, the black means midnight, and then the red ones are the morning and the blue ones are the afternoon. So you see that obviously we are going around the same temperature, but with the air, we have a temperature difference, intraday temperature difference that we do not have during the in the sea. There, I computed the difference between the sea temperature and the air temperature. When it's minus, that means that the sea temperature is colder than the air temperature, and when it's plus, that means that the sea temperature is hotter than the air temperature. So what we see is that the difference is much lower than in a tropical SWAC. In a tropical SWAC, you get water that is 4 degrees with an air temperature that is around 30 degrees. So you have more than 25 degrees of difference. Here we are somewhere between 8 degrees and -6. But notice again that during the summer, the hours where there is the biggest temperature are the noon and the afternoon. And during the winter, the hours where there is the biggest temperature are the night hours and the early morning. Now let's speak about the Newlyn site. You see that Newlyn site is completely in the end of Cornwall. So they are our twins as we are in Brest. They are as much in the end of the Earth as we are today in Brest. And they are in Penzance Bay, and the site consists on 2 containers on the south dock, and the containers, inside the containers, there is all the devices for the lobster
Lobster hatchery.
Hatchery, for the lobster hatchery. So they pump water for their process of hatchery because they always need fresh seawater so that the baby lobster can grow up in the hatchery without being harmed. And the incoming pipe is going along the quay until the containers, and then it's used for the process, and the water is rejected in the sea just close to the containers. So for the moment, this water is took, but it is not used for thermal process. Here you see that the depth of the sea is not as interesting as it can be in tropical islands. We cannot go to deep sea. So the only thing we can do is use the water that we have close to our site. So now let's see a few pictures. You see a picture of the abstraction pump, and then pictures of the pipe network, pictures of the different filters, and you have the ultraviolet system also, and then the real hatchery process. This is for you to have an idea of what happens inside these containers. And here are the areas of improvement. The first one is for sunscreens and trickling. The second one is heat pump and chiller. And the third one is enhanced pumping, but I will not talk about the third one today. When we saw the difference between seawater and air water, there is something we completely forgot. It's that during the time where the air temperature is hot in the summer, there is a high rate of sun rays that heats the containers, and therefore the surface of the container is much hotter than the air. So we have, during the summer, we have to the air conditioning system must face first the temperature of the air that might be too high, but second, and this is the most important, it must balance the rays of the sun that are going on the container. And so when there are rays, if you see on the left, you see the two containers, satellite image of the two containers. And in the middle, you have a scheme of what happens. The rays are going on the container. There is one part that is refracted from the container, and the part that is not refracted is converted into heat. And this is what makes the metal of the container become very hot. And on the right side, I computed the amount of heat that is generated just by the sun. The one that is on the bottom is the amount of sun rays that are received by both sides of the container, the south face and the roof face. I didn't compute the other faces because they receive very little. And on the graphic on the top shows how much of this energy received on the container is transmitted inside the container. And you see that in a hot day, you will have between 40 and 50 kilowatt hour per day that is transmitted inside the container. So it's a lot of heat. So the idea was to make a mixed system with sunscreens that do not allow the rays to go on the container, and a coil that you see the blue coil that is fixed on the container to reduce the temperature of the container itself. And this is a way to use directly the water that is going on this coil is just plain seawater, and we can use it because the temperature of the surface of the container is much hotter than the temperature of the air. If it was just at the temperature of the air, it would not be enough. So with this, we can have some kind of free cooling. I did put again the graph with the temperature, the difference, the temperature difference between the sea and the air, because on next we are going to talk about heat pump and chiller. Heat pump and chillers, their efficiency relies a lot on the difference of temperature between the source of temperature heat that we have and the temperature we want to reach. the difference between these two will give the efficiency of the chiller. So this difference, what is the interest of having seawater instead of air? As we saw that there is very little difference between seawater and air. The first interest is that, as we saw on the graphic, on the hottest hours in the summer, which are the hours where there is the biggest demand in air conditioning, then the difference between water and air is quite important. It's about 4 degrees. That means that we win 4 degrees and we win in performance of the chillers. And the same, but reverse, for the coolest hours during winter. So the first thing is that during the times where there's the biggest, most important thermal needs, then the gain with seawater is more important. Second one is that the quality of the exchange with water is much better than with air. And third one is that with water exchanger, we can get rid of fine coils because fine coils in a marine environment will get destroyed very fast, and it can be a big problem with the. Thank you very much.
Okay, thank you very much for this. It's a very interesting outcome there from the study there regarding Lobster Hatchery in Newlyn. Any question from the floor or from the online? I don't see anything in the chat box again.
Maybe one.
Yeah.
We know for such a study, what is the time required for you to have the complete assessment of what is needed in the site?
Usually, if we are talking of there are several levels of study. The first level of study is feasibility. For the feasibility, it's about 1 month of work. Then second level, when I say 1 month of work, it cannot be done in 1 month because there are exchanges. We are looking for information, and there is all the time for information exchange. For the second part of the study, what is the basic design? We need about for different projects, it will be different. I just give you an order of magnitude. It's about 4 months for the basic design and about 6 to 9 months for a detailed design. If we are speaking about small project like those, if we're speaking about a bigger project or a tropical project where we have other issues because the pumping pipe is much more important, and then you can multiply by 2 or 3.
And for the procurement and production,
it depends.
Let's from this project, for instance.
Yeah. It depends really on the way you are doing the procurement. If you want to make a European call for tenders, it takes lives. If you can make an easier bid, the procurement can be done in 6 months. But usually the critical way in the project is the environmental studies, because for these studies in France, usually we need about 1 year, and for doing this study, you must do quite a lot of studies, of design studies, but you must do these design studies before you know if your project will be allowed or not allowed. So it's quite difficult because usually people who pay the project agree to pay money, but when they are sure. And here it's a part where they have to pay money without being sure.
So, but just at a glance for a customer on a small project like that, the order of magnitude is 2 years to get the product.
In France, yes. In England, the environmental studies are easier than in France. As I understood.
Okay, thank you.
You're welcome.
Okay, any other questions? Otherwise, I have one maybe. I think so, yeah, it's with having the containers there and using the sunscreen as you're proposing and the cooling as I think it's a very cost-effective idea, I would say. So you don't need an additional cooling systems there, heat exchanger or so. What would you use in terms of the sunscreening? Would you use particular insulation material, or what would be the the materials to make sure that it's efficient, I guess? Otherwise, you're heating up your water in the pipes, I guess. So what would you suggest then in terms of the cooling, the sunscreening element?
For this project, the idea would be to have sunscreens and then and a space for air to be able to flow, and then the container. The sunscreens will not be touching the container. So we do not any isolation material will not would not do anything good, because the isolation is for the conductive to avoid conductivity, thermal conductivity, and there we do not have conductivity. We just have air that passes. So what I suggest is just a metal foil, like those that are on the top of the buildings, because the advantage of those is that you find them very easily. You can have people to cut them because they are used to it. It's very important on this little project to use the most common materials. And when there is one that is rusted or needs to be changed, you go to the local hardware store and you can change it.
I think very, very cost effective for sure, and very clever in its way to achieve a cost effective SWAC system. So well done for this, I think. So any other questions? Otherwise, I think so we are moving on to the next presentation. Okay, the next presentation is more on the innovation part. As will be presented, I think, by Claire Perez. And so on the flexible pipes, part of the innovation element is in EuroSwac. So, yeah. And sorry again, we do have some technical issues here constantly.
Yes, I apologize for that.
The interesting thing is you don't see it, but practically every 5 minutes our screen is disappearing here, so and we have to fix it again. So. Okay.
Can everyone see the presentation?
Okay, over to you, Claire.
Yes, so good morning. I am Claire Perez from Doris Engineering, and I will present you our work about the hydrodynamic behavior of the flexible pipe. I will share this presentation with Alexandre Fincinello from OCM. So, as reminded by Lars this morning, the SWAC is facing a CapEx challenge because of high material costs, an expensive shore approach protection, and a high cost of water installation. So, one objective of the project is to reduce this CapEx. Okay, so last time we presented the first innovation, which was the self-bombing pipe, and today we will focus on the flexible pipe, which can improve CapEx with regards to the pipe material. The flexible pipe is less expensive than the traditional pitch pipe, and it improves as well the cost for installation because we avoid connecting the rigid pipes by using a flexible pipe on a mill which we can deploy at once. So this work is part of the second task of the project. So the problem we have is that the software we have for pipe design are not made for flexible pipe. When we perform our first calculation, we use different softwares and we obtain different results. So our strategy to overcome this problem is to perform model tests. And the final objective is to provide data with this model test to validate our numerical model and to develop a reliable methodology to assess the behavior of the flexible pipe and, in the end, design a complete SWAC system. Okay, we go to the next one. Our program for this work is first to have a preliminary flexible pipe design on our CapEx software in order to identify the different configuration and the key parameters to play with during the model test. And then we will go to the model test, which are currently ongoing in the CLI. And the objective of the first campaign is to calibrate the numerical model based on the experimental data and refine the conceptual design and define the next research. Okay, so the next test campaign started on the 20th of April. 80 tests are planned. We will play with different configuration based on these parameters. So the wave incidence. Go to the next one. So we'll have inline waves, transverse waves, and water waves. We have regular waves from 4 meters to 10 meter heights. We have current, underwater current. We will have different buoy configurations, cylindrical buoys and circular buoys. Buoys, we will play with the buoy distribution along the pipe, 10 meters and 20 meters spacing. We will have different end configuration, either fixed ends or fixed and free ends. We will have different internal pressure, different water flow rates, different sling stiffness. The sling is the line between the flexible and the bottom, the flexible and the voice. And in the end, we will post-treat the following results: the motion of the pipes, the tension in the slings, the tension and compression along the pipe and the bending radius along the pipe. This is the program. Alex will speak about the fun part, which is the test.
Yes. So the basin test is performed in the PGO first, so the shore basin located in Bassin-sur-Mer, southeast of France. This basin is operated by Oceanide, and its main dimension is 14 meter long and 16 meter width. And it is equipped with a movable floor, so we can adjust the water depth from 0 down to 4.8 meter depth. And in this basin, we can generate both wave, current, and wind. So the main objective of the basin test is to test the flexible pipe in the basin in order to provide experimental data to Doris engineering to validate and calibrate their numerical model. So to do so, next slide, please. To do so, a flexible pipe is installed horizontally in the basin. So the flexible pipe is fixed at both ends. Okay, let's see here. But it is anchored to the basin floor using a vertical sling, so just below the pipe. And some buoyancy modules are attached to the flexible pipe in order to avoid the pipe to touch the basin floor during the test. And during all the tests, the pipe is full of water, and we can adjust the internal pressure and also the water flow rate. So the selected scale for the test is 1/20. During all the tests, the water depth is set to 15 meters, so full scale. So in the basin, it corresponds to 2.5 meters. And the main dimension of the pipe is 150 meters long, and with an external diameter of 1.4 meters. So this is at full scale. So again, in the basin corresponds to a pipe of 7.5 meters with an external diameter of 17 millimeters. Okay, during the test, the pipe will be submitted to the action of wave only, current only, and also the action of simultaneous wave and current. And here, maybe if you can see, no, you cannot see. Okay, so normally it's a video of one of the tests with a wave 8 of 8 meters per 11 seconds.
It does work. They can see it, but very, very slowly.
Okay. So normally you can see the wave passing on the pipe, and you can see the pipe motion. So
You can see it, but very slowly.
Let me try something.
so next slide, please.
I can see it.
You can see it, yes. And you can see
People online can
you
see
can
it.
see pipe motion. So
It's slow, but you can see.
Oh, yeah, yeah.
okay, and during the test, several measurements are made. So first we measure the tension in the sling at 4 locations, so both at the anchor slings and at the buoyancy slings. The reaction forces, so the 3D reaction forces at both extremities are also measured. And we also use underwater cameras to track the motion of the pipe. So these 4 cameras aims at tracking 7 targets located along the pipeline. And jump to the next one. So this is location of the 3D load measurement at the extremities. And in the next slide, yes, so here you can see one of the underwater camera. So again, there are 4 underwater cameras, and the location of the 7 targets along the pipe. Okay, I do not have a video, but you have here some pictures. So on the left, you can see the pipe installed in the basin. On the middle one, you can see the pipe with the basin floor at its top location. So we can have access to the pipe to perform some modification. The top right picture is maybe see a wave passing on the pipe. And the last one is the pipe during installation. And you can see the 4 cameras used to track the motion of the pipe.
Okay, and now for the first results, which are preliminary because the tests are still ongoing. So what we can say it is the results are promising. The motion we observed are the one we were expecting. The loads we observe is the load we were expecting. So you can see a graph with 2 curves superposed. The numerical ones in dotted lines and the experimental in full line. So it is same order of magnitude. That's all.
On the next meeting, we'll have the results to present.
Oh, but these ones are.
Because I'd like to have 2 days of tests.
So the perspective for the second line will be to carry out physical model test on a more realistic flexible pipe configuration. For instance, instead of being fixed to the bottom of the basin, it will be fixed to a ballast line in reality. We will have better insight of the behavior of the flexible pipe bed on the seabed. And in fine, we want to size all the components of the design, the weight of the anchoring system, and the buoyancy modules we need to have in order the pipe to go on the seabed, and the sizing of the slits. Thank you very much.
Thank you.
Thank you very much for the very interesting presentation on the innovation part. Questions from the audience? Again, I don't see anything in the chat box, but please feel free to raise your hand.
The pipe is flexible, but is it pressure resistant or is there a pressure inside the pipe or?
Yes,
Yes.
there is a pressure inside the pipe. If maybe we can go back to previous slide, we have the order of magnitude. I think it's
Yes.
it's 2. We have a pressure of 2 bars in the basin, so we're supposed to 40 bars.
Yes, 10 to 40 bars.
Which slide, sorry?
That means it will be used with a submerged pump at the end of the pipe.
Yes.
When you say that the pipe is flexible material, it's a bit rigid like PhD.
It's in polyurethane.
We know that for SWAC, the most important constraints is about the installation. During the installation, is it only, are you studying that?
Doris, I think.
Made some studies, but not with the EuroSwac project. We did a study for ClubSWAC, and we observed again the installation for flexible rigid pipe because we avoid connecting the pipes.
During the installation.
We can have some flexible pipe on a reel, so we can have more length. We don't need to connect as much. We have the first slide on this. We have a view of the installation process.
In terms of cost savings, it's probably quite difficult to put something against it to anyway, to sense. But do you have any kind of estimation? What is flexible pipe? You know how much is?
On this slide, it is an estimate for a tropical SWAC. I can't read, I'm sorry. We gain 4% of the total capex just for the material. We gain 5% of the total capex for deep water installation. In the left part, you have a view of the installation we anticipate with the deployment of the flexible and the ballast at once. In one.
You made this comparison on what that.
Tropical SWAC study we performed 5 years ago on the SWAC in Kingston.
So there's a traditional fixed steel pipe compared.
Exactly, traditional 18 long, it's a little bit.
Because actually there's only 3 SWAC working in Bretagne.
Yes.
So are you sure about the data and figures?
It was the best data we had on time.
Okay. Any more questions? Otherwise, I think so. We may be moving on. So the next presentation will be by Ola Zavalana here. It's the 4th part and the final parts there on the optimization. So Ola, I think so you will drive the slides yourself, or you have some difficulties here. So hopefully it looks better if you will drive the slides yourself. Yeah, we can see it. Yeah, perfect.
Perfect.
Ola, the floor is yours.
Thanks. Good morning. My name is Ola Zavalna Gier, and I am a research fellow at the University of Exeter. I'm working on replicability study. Unfortunately, I cannot see the screen for some reason on this laptop where the camera is, so I will be looking the other way. It's not that I'm rude, it's just I cannot see. Anyway. So today I'm going to present to you SWAC replicability requirements, and I start to show the very simplified SWAC system diagram on the left here. So these are all components needed for the SWAC design. Also on the right, you can see how it can be optimized and what parts are needed into optimization. And here we have the technical requirements, which are obviously probably most important ones. Then we have the environmental studies and the financial analysis. But as we can see on this diagram as well, that they all overlapped each other, and in a very, very middle is the replicability, and the replicability will need all those parts to actually work and find the optimum SWAC design for the particular location. On the left here, we have the channel, and we have all of the eligible regions for the SWAC. Of course, we need location close to the coast, so some of those regions are totally not applicable, and we are not going to consider them at all. Jamie prepared here a very good map, and it's on the right, and it is with all location which we already identified for potential end users. So we can see that on all eligible areas, we have quite good density of potential end users. Those all end users were categorized because obviously the SWAC system will not work the same for every end user, because every end user will have the different requirements for the cooling. And of course, once you have the end user, you are doing it individually for them. But for this particular study, we had to categorize them to make some optimum for each. And we categorize them in many ways. So there are hospitals, there are hotels, there are aquariums, there are data centers, etc., etc. So first, I already mentioned that probably the most important part here for optimization are technical requirements. And we identified five main components for the optimization, and this will be optimized as an object-oriented optimization. And here we have intake depth. It's obviously very, very important because based on the intake depth, we will have the different components will depend, like intake length and head loss as well. Then we have the heat exchange area, and I called it here heat exchange area, but really we are looking at the heat exchangers. And talking about the heat exchangers, we are looking at the position of heat exchanger, number of heat exchangers, maximal flow for each heat exchangers, also automatic filters, how many, where, size, etc., but also how much heat is being exchanged. And here we have, I assumed above or equal 0.5. We are for optimization doing 0.5. And this is because we cannot reach very cold water in the channel, and this is probably our optimum. Then we have the SWAC maximum thermal power. So obviously, for each individual site, it will be SWAC will have the optimal power, and we are in the first phase. We are looking at the two scenarios. So one is with the chillers, and then is with the SWAC, and based on it, we can calculate the best or the maximum thermal power. And it will depend on a few things. First of all, it is maximal customer cooling need, then what's the targeted delivered temperature, and few more, as we can see. Then having the thermal power, we can calculate the cooling power, and based on the cooling power, we can calculate the expected flow rate. Expected flow rate, it is needed to establish or optimize the pipe diameter. It's very important to know what diameter it is, because flow rate will relate to heat exchangers, pumping system, the length, etc., and the biofouling as well, to prevent biofouling. And then we have pumping system. So again, we are here looking at if it is already pumping system, because many sites may have already air conditioning cooling systems. So it can be something already existing, which we will try to adopt for the SWAC system, or we will start from the scratch. So again, pumping system, it will be location, if it will be over or under the water, the type, capacity, those kind of things. Then environmental requirements are obviously very important as well. And here we identify three main, and it's local bathymetry, because on the bathymetry, we will look into the optimal intake depth, optimal intake length, but also how to install all of the geometry of the bottom of the channel where it would be installed. Then the thermal gradient of the seawater, it's needed for estimation of the cooling power available for individual SWAC, but also we are looking at the surface air temperature. So this is another very important parameter. So these are three most important, but of course we have to look at other things as well. And other things are more like on the traffic light system. So if it is something feasible, and it's definitely yes, we will go for it. But if it's not, we will look if we can optimize it, if it can be improved. If not, we can just totally ditch the idea. If it is improved, we have to see how much and how much it would cost. There are all the parameters as well, like constraint parameters will be thermal discharge and mixing zone, but they are very important for each SWAC system. We will have to look at environmental constraints. So we will have to look at the tides and currents, because it will be important for the installations. Then we will have to look at the mandatory regulations, but this is different tasks, so I will be just getting the information from there. And environmental impact assessment, again, this will be something what is already done, and I will be just gathering the information. So first thing I am doing, it is in the progress. I thought it would be a really good idea to create a map for the whole channel to see where the SWAC has potential. So we have all of the end users, but now we have to see how applicable SWOC system would be for them. We're starting with the three main things, and we are doing the maps of the seawater temperatures, and I'm doing the sea temperatures of temperature of 15, 10, and 5 degrees of Celsius at a different depth. So starting from very close to the coastline, 0.5 meters, and going all the way to 50 meters, but they're very optimistic. I don't think we will go that deep, but just to check. At the end of the day, it's just a study. Then we're doing also topography of the shoreline. And here, again, maybe I am a little bit too optimistic, maximum 10 meters. But again, this is just a study. But also this shows why we cannot take all of the eligible regions into considerations, because it has to be close to the coastline to be efficient financially. And also bathymetry of the channel. This is very important because we need to see the geometry for the installation, but also to see how long, where's the intake depth, how long the pipes need to be. And all three components will go into the locations maps with temperatures 15, 10, and 5 degrees of Celsius. And we will be looking, again, very optimistic, up to 1 kilometer from the shore. But it has to be efficient financially, so probably it will be less than 1 kilometer. Then this kind of information will go into another. This will be input for another component, like length of pipeline to reach depths with temperatures of 15, 10, and 5 degrees of Celsius. And again, they will be shown as maps. In the meantime, I will be looking also at the hourly air temperature, and I will be looking at the temperature of 15, 20, 25 degrees. It may be hourly, but actually just looking at this Bruno's presentation today and him doing it by 3 hours, maybe I will change it to every 3 hours, and it can be totally sufficient. Based on this information, I will be able to calculate the SWOC capacity factor and again make the maps. And this, as well as the length of the pipeline, will be input to compare the shortest pipeline with the capacity factors and the depths with the temperature less than 15 degrees of Celsius. Having this information, I will be able to estimate the SWOC cost for the whole channel for all coastline. So this is the idea. This is the progress. The whole work is in the progress. I think it can be quite interesting, and I will be very happy to show it next time I'm presenting. And the last part of the replicability study will be multi-objective optimization. So in this case, we'll be optimizing how to make SWOC cost efficient, but also environmentally friendly. And of course, you cannot satisfy everybody. So we will find the different solution, and it will be multi-solution, and the potential future end user will be able to look into this optimization and choose where they want to be, what solution is best for their site. And to do so, this will be there is already code ready in MATLAB, but this is planned, not in progress yet. And here I already discussed it with Jamie. Jamie, can you take over?
Sure, yes. So my name's Jamie, and I'm based at the University of Exeter Business School, and I'm working on T4 as well as part of the market study and potential business models for the upscaling of the SWAC systems. As Ola's mentioned already, we've been Ensta's been leading the potential site studies for short-term application sites within the project. And on top of Newham and Brixham demonstration sites, 6 sites have been identified. 1 has confirmed they'd like to study on their site, and a further 4 have expressed their great interest and should soon confirm. And we also have 1 which we're waiting to hear by. We're aiming to have a definitive list validated by the end of June. We're still always on the search for further application sites in case some of those additional sites stay there. Thank you, Cameron. Oh, no, next slide.
Yeah. Here you go.
So I'll just there's a lot of information on the table there. So I'll give a brief summary as to how we are developing a potential future business model for the upscaling of SWAC. Starting with the columns up there, we are looking at various usage models and comparing against other scenarios. So the usage models we're looking at on the left-hand side is no SWAC, or traditional air conditioning system. And then in the centre there, we're looking at a SWAC system as we're modelling at the moment. Then on the right column, we're looking at a circular SWAC system. Now, to give a brief introduction, whether we make a SWAC system at the moment or in other sorts of similar process and engineering, may make also a linear model that we take from the environment, produce a SWAC system, for example, then in this life cycle, we may dispose it and throw it away. The circular SWAC system on the right-hand side of this table, we're going to have a look at the usage model where we produce a SWAC system, and at the end of its life cycle, we don't throw it away, we regenerate it, refurbish it, and we can try and use it elsewhere. So those are the three usage models that we're looking at. And we're also looking at two separate scenarios down the left-hand side, where we're looking at the optimized model, which Ola is working on. And then on the bottom scenario, we're looking at alternative materials. We may swap out a couple of materials in the SWAC system in order for more durable alternatives, in order to further extend the life cycle. So basically battling against the short-termism which you may encounter in engineering, and seeing how we can again extend that life cycle. And then the way that we're modelling these, we're using three separate methodologies. And we are measuring the environmental impact, the economic cost, and the social impact of each of those three models against both scenarios. So with the top scenario, I'll briefly summarise. With no SWAC, we might move from an altered environmental impact and a standard economic costing on a traditional air conditioning unit with little social impact, moving through a SWAC system which we're optimising at the moment, where it anticipates an improved environmental impact and optimised economic terms through capital expenditure and operating expenditure, and social benefits drawn through improved quality of life and creation of jobs. But if we get to a circular SWAC system, again, we'll have all of those environmental and economic and social benefits on a traditional SWAC system, but enhanced through reduced extraction of resources, because we don't need to take quite as much material to make a new SWAC system at the end of its service life. We're reducing costs through regeneration, and we're sustaining social benefit for expertise, labour, creation of jobs and upskilling up the supply chain, and awareness of sustainability, and even more improved quality of life. And then in the bottom scenario, again, if we use those same methodologies to move across the right side of the table, again, on the left-hand side, we might have an altered environmental impact. We might have an increased capital expenditure through the use of more durable or slightly more expensive materials, but again, you have a longer life cycle. You'd have little social impact, of course, with the traditional air conditioning system. But then as we move across to the right, again, we start to see all those improve. So with a more durable material-based SWAC system, you have improved environmental impact and a further improvement for more durable material. Again, the financial terms of SWAC would be improved, and social benefits would be drawn through improved quality of life. And then with a circular SWAC system, with even more durable materials, again, you would be seeing more significant environmental improvements through reduced extraction of materials through reused or durable materials. There might be an initial capital expenditure increase, but you have a longer life cycle optimised through more durable materials. And again, you have the same sustained social benefit through upskilled labour, job creation, and improved quality of life. So hopefully that explains it, summarises it quite well. And from those three usage cycles, we'll then create a business model which we hope we can use to upscale SWAC in the future. Next slide, please, Ola. This is, so we've talked about, I've talked about the environmental, economic and social methodologies which we're employing. This covers very briefly the economic life cycle costing. So we'll be deploying a life cycle costing methodology to assess the economic cost of air conditioning options within those scenarios there. Using it to work out capital expenditure and the operating expenditure, as well as maintenance and disposal, and in the case of circular SWAC, regeneration cost. We've taken into account all those aspects down the right side of the diagram there. So I'm looking at maintenance, repair, the admin which may be required, as well as the discount rates of the future, any revenue that comes in, And what we'll be doing is comparing the economic cost of each scenario to generate a sort of a comparative payback period, which again tells us the most cost efficient, cost innovative usage model to develop a business model from. Thanks, Ola.
Okay, so yes, thank you very much. Any questions?
Okay, thanks a lot. Those was a very interesting overview in terms of optimization and how it can be replicated, I guess, across the channel. Yeah, as always says, any question from the audience, either online or from the room here? Otherwise, Ola, you mentioned that you have to look at each SWAC system individually. Would you see this as a cost-effective methodology, or would you think that you're trying to develop a kind of characteristic SWAC system, say what you could implement? So you have a more serial production there of some of the SWAC system instead of starting every time with an individual design. But maybe Bruno also would like to come in on this one. But first, maybe Ola, what is your view on this one?
So this is why why I thought that. Can you still see my screen? Yeah. So this model framework. So I am fan of going from the big thing into the smaller things, tinier. And this model framework will work for the whole channel. So firstly, it will show how cost effective. That's why we are finishing with the cost estimation for each SWAC. So it will be shown for the whole channel. But of course, this model framework can be used as well for each of our category, and it can go down even further if we have the individual end user. So this can be calculated individually for the site, for the location. If it is cost efficient, well, it will depend on where it is and how we calculated it when we have already end user.
I guess it's also demand dependent as well.
Yeah.
And it's identified for Lobster Hatchery, maybe some modifications or some clever thinking, say this way, is also required to make it possible.
Yeah, so this is what we can see right now on our demonstration site, and this is something what Bruno already said, that there are ways of optimizing it and finding it to make it improvement and enhance the SWAC system financially. So yeah, we are starting from some big picture, and we can go down to this will give us the big picture, how it can look like cost-wise, but it can be in each site, it can be improved, and we will find the components to add it to improve on each particular site.
Oh, absolutely. Jamie, you identified a couple of sites there as well. So what is the general interest in taking some SWAC systems? There is this quite a positive engagement with this.
So we've been seeking to engage with potential end users. We've engaged with a large supermarket chain in the UK, and they felt that whilst they found SWAC technology interesting, they'd like to see more data on its usage within a retail environment. And we've also managed to engage with a luxury hotel resorting board, now very interested in the innovative technology, particularly as sustainability for those industries is a key metric as part of their key performance indicators as they seek to become more environmentally sustainable, particularly as their customer base may be having a more growing awareness of their carbon footprint. So the SWAC system very much represents a exciting opportunity in which business can improve their sustainability footprint.
So what I'm hearing here is that this demonstration sites, I think, are quite important to provide some data about what saving potentially could be and what the impact for the business would potentially be. So, right, so okay, it's very good to hear.
I have just a question.
Yeah, certainly.
Now we have a lot of facilities that when we have seawater treatment in order to drink, is there any collaboration with these facilities to have SWAC inside these facilities?
I don't know if Frank want to come in here at this point, maybe.
Yeah.
I don't know, Frank, if you want to come in, or Bruno, of course, as well, but.
Could you repeat the question? I'm sorry, I didn't hear properly.
There are some countries that use seawater to produce drink potable water. There are huge facilities, surely need air conditioning systems. So is there any collaboration with these companies?
I think it would more be for you.
Yeah.
Frank, I mean, I think so, you know, it's not this, the drinking water, but again, there's a different application where your SWAC system is integrated there. So I don't know if you would like to comment on this.
Since we have an intake of water from the sea already available, so is the capacity. No.
Yeah, well, I'm not sure if this will properly answer your question, but looking at alternative sources of energy is something we have to do constantly now in the university. It's the University of Plymouth, but I'm sure it's the same in lots of places. So, for example, this is slightly off topic, but we're right now about to replace some 30-year-old gas boilers, and rather than just jump to more efficient gas boilers, we're doing a feasibility study of alternative heating and cooling sources before we can make that decision. So as you know, and you can see behind me, we have a big pool of water that we can use to heat and cool, and we are actively considering that as a solution for our energy needs in the future. So whilst we're a demonstrator site for this project, for a relatively small part of the site here for a SWAC system, we are constantly looking at greener technologies to replace less green, like gas, and equally, you know, gas is obviously an interesting topic of conversation at the moment too. So there are many reasons why we would want to consider replacing it going forward. So that, I'm not sure if that really answers your question, but it just gives you a flavor of some of the things we're thinking about here.
I think the fact that what comes in is a dual usage, maybe, you know, it could be drink water, but in a way, I mean, it's providing.
I'd like to jump in on that because I came here, I work in a startup we developed in southern Britain, a new system to desalinate water and create potable water. So I was here today to see if there is a possibility to use the same intake. We've been contacted by French Polynesia. That's why I've seen this one. So to use the same intake of water, to use the water after the cooling of the hospital in French Polynesia, to then go over at least into the system to create water. That's what's the idea.
You want to comment on this?
Yes, this is very important. Every time we are working in a SWAC system, we try to have water having 2 or 3 different lives. One life where it is used because it's seawater, for example, in aquaculture. A second life where it is used because of its temperature, and maybe a third life where it could be used by removing the salt and making drinkable water. Because the fact of having several lives for 1 liter of water means that you, with the same energy to pump the water, you do three things instead of doing just one.
I think there's dual usage. We looked at this with other end users already there. There will be aquaculture elements there, national Hatchery as well there, because they're needing the cooling, but also they're needing the water intake to filling up their tanks. So it's not use of water treatment or anything, but the needing water for the lobsters there. So it's a dual usage, as Una is saying, I think. So it's an important element to make it cost effective, certainly.
For that, and especially in some countries, like we have that's also in like African countries where they have those two things, and it would be, but it's expensive even for the desalination. So neutralizing, the same intake would be ideal. But is it feasible technically or not?
I will be happy to talk about this, but this is not our region. We are talking about the Channel area. So let's keep on our region, but afterwards, I will be very happy to talk about it.
I also see two hands up there. Jishu, will you go first?
Yes, hi. Thank you. I think the idea of reusing the water as drinking water, I think that is a very interesting idea. It's certainly something that University of Plymouth will be very interested in because of sustainability and thinking of circular economy as well. So it's we will be happy to discuss the idea with you further if it's something that's worth pursuing. So we are keen to explore other uses of the water that we've sucked in and used, and then if it could be reused for something else instead of fisheries at the moment, but any alternative ways of making use of the resource is very useful indeed.
Okay, thanks. And Guy Bardot.
Yes, I would like first to thank a lot to all the engineers who have performed this very interesting topics. And so I am the president of the Value Park company, and Value Park is a developer of SWAC. And so we at Value Park are very interested into your studies. And so I would like to encourage you to have a contact with all the team of Value Park to give a follow-up to your job. And thank you very much for all the hours you spent to do your job. Thank you very much. And I would like to apply your studies, the results of your studies in a real project. Thank you.
Thank you very much for the very positive comments there. Yes. Okay, I think so. We're running a bit out of time.
Yes, and I'm sorry. Some people have trains and ferries to
catch as well. Yeah.
But some of us can stay a little bit more if you want. If you have some questions, I want to say thank you to all the speakers today, and thank you to all the attendees. That's really great for us to see interest in our project. So thank you very much. Sorry again for the technical issues. And yes. And just a reminder that the EuroSwac project will also be at the Synergy conference in June and at the CTEC week in Brest in September. So if you want to come and see us and discuss more, we will be very happy to meet you there.
Yeah. And just adding on, I think so. You have a website, we also LinkedIn. So if you want to follow us, latest results, videos, etc., please make sure you go to our website or look at the LinkedIn. And you also very much and appreciate your comments. So if you want to get in contact, please send an email to us, and happy to discuss with you any ideas or applications in the future. So I think I would like to bring it to an end. Thanks again for all the speakers and for attendees that are coming here. So thanks a lot. I said we are online and we will inform you about the next event, what will be happening, I think, time, as well as, of course, events we attended. So thanks a lot and goodbye.
Thank you.
Thank you. Bye.
Bye.
Thank you. Goodbye. Bye.
Thank you.
Bye.
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 Thank you all. Bye bye. Au revoir.
Bye.